Okay, thank you. Thank you for your patience, everybody. Welcome to today's lecture. Today we'll be talking about logic tensor networks. A brief overview. First, we will be discussing real logic, which is the underlying fuzzy logic in this framework. We'll be discussing briefly a little bit, recalling what tensors are, what groundings, and then the fuzzy operators that are the basic machinery underlying this. Then move on to logic tensor networks, or LTNs, and we'll see how we move from real logic to this framework, and then what kinds of tasks, the main tasks that we have in this framework, and then discuss a few use cases. And then if we make it, I think there'll be enough time. If not, you'll have the lecture notes, but as a little bit of bonus material, what conditions we have for all this to work, which is for the fuzzy logic to be differentiable. So as an introduction, you can see that LTNs are a recently developed framework based on, as I said just now, fuzzy differentiable logic. And the goal of this proposal is to support tasks that require a deep connection between data and knowledge. So we saw a little bit about this in past lectures, also in the introductory ones, but here we'll see that we're going to go a little bit further. So the formalism has been shown to be very good at tackling different tasks that are central to intelligent systems, like multi-label classification, relational learning, clustering, supervised and semi-supervised learning, regression, all of the basic stuff, and also query answering under uncertainty, which I spoke to you about a couple of lectures ago. So let's get started with the underlying formalism, then real logic. It's not that other logics aren't real, but this is based on real values. So the fuzzy logical language is infinitely valued. Domains are interpreted typically concretely by tensors in the real field. It just means that, if you recall the introductory material for this course, tensors, they sound fancy, but they're no more than no less than algebraic objects. So if they have dimensions. So if it's a zero-dimensional tensor, we're talking about a scalar, just a number, a value. One-dimensional tensors are vectors, what are commonly known as vectors, and two-dimensional ones are matrices, so those rectangular or square arrangement of values. And when you go beyond these very simple examples, we have higher dimensional structures, which are generalized tensors. So because these domains are interpreted in this manner, the authors use the term grounding instead of interpretation, which is the usual name for the concept in logic. And we'll use this calligraphic letter G throughout the lecture to denote what this concept of grounding. So what are we talking about specifically when we talk about groundings? They're essentially mappings. So it maps terms to tensors of real numbers. So terms, if you recall, are what the underlying basic building blocks of logic. So if a constant is a term, a function applied to a constant is a term, a variable is a term. And the grounding also maps formulas to real numbers in the real interval. So value between 0 and 1. And from now on, the correct way of saying this would be tensor in the real field, but to be less cumbersome, we'll just say tensor. And as usual, as any logical language typically has, we need to support connectives and quantifiers. So we'll see a little bit about this in a second. First, the most basic stuff, the constants, as usual, also denote individuals. a space of tensors. We have this this formula here. It's just saying, for this, it's just saying a tensor of any rank to denote this complex expression. It's just saying this simple concept. And the individual can be either predefined, which is a data point, something that I've already observed, or it can be learnable, which is the bread and butter of machine learning approach, right? Embeddings. And the intuition is that each dimension corresponds to some feature of this individual. We'll see several examples of this, both kind of abstract with letters and also towards the, as we move on later in the lecture, we'll see use cases. But so we have dimensions that have mapped to features, and the number, the value in this assigned to this position corresponds to the value of that feature for that individual. So if I had, let's say, an individual which is a dog, we could say that we have several features such as the dog's gender, maybe the kind of dog, if it's if it's hairy or non-hairy, that kind of thing. Okay. Variables denote sequences of individuals. As usual, variables can take different values, and we are interested in representing all the possible values that the variable can take. And these sequences can contain more than one instance of the same value, just to be general. Okay. Moving on to the higher level concepts, functions can be any mathematical function. Also can be predefined or learnable. We'll see that it's very powerful formalism that can have both predefined fixed functions that you want to always behave in the same way, or you might want to be have the capability of learning this function. And the same for predicate. So an example of a function is a distance function, for instance, something that you always want to calculate the same way, or a regressor, which is something that you might want to learn. Predicates are essentially the same thing, but as usual in logic, we have a mapping of an n-ary domain interpreted to a real value, just a single value, interpreted as a truth degree. Okay, so examples of predicates: a similarity measure. Similarity measure might just take two objects and say how similar they are. So that's just a mapping. It's a special kind of function that will map to a value between 0 and 1. Remember that we are dealing with fuzzy logic and not crisp logic. So if this generalizes the crisp logic, because if I would only map to 0 or 1, I would only have two values. Okay. Another example, classic example, the same way that we said that regressors are a kind of function, classifiers are a kind of predicate. Okay, so if you want to classify something into one or more classes, then you will say which degree of truth an individual has, depending on the class. So this is an example of a visual example of how this is everything I just said essentially. So here we have individuals, so represented as a vector of values, each one for each feature. So in this case, we have a 3-feature vector. Here we have another one with only 2. Let's say we have a function of these 2. And here we have then the grounding. So the grounding of this individual is, of course, this sequence of values. The same for this. But here is where it gets interesting, because we see that the function is mapping pairs of values. So that's why this tensor has now 2 dimensions. Okay, and the depth here is just the result. Okay, the result of the function. So one for the authors call this the feature depth. The feature depth. And so in this case, what we could do is look up, say, depending on the values of this, we have a lookup table with the input, and then going in the third dimension, we have the result. Okay. Similarly for predicates, in this case, it's taking the output of the function and just also passing through the x. We have the same thing. So here we have p of x, the direct path, and then f of xy, which is this output, and we are getting a result. So connectives then are modeled simply using fuzzy semantics. So we have conjunctions and disjunctions. These are typically, we'll see a few examples of this, but conjunctions generalize are generalized forms of the first order conjunctions, and they are represented by T norms. The same, the disjunctions with T conorms, and these connectives, usually the fuzzy operators take the letters that I include here. For implication, sorry, is there a question?
Yeah. So in the previous slide, the absolute right. So I thought that the predicates shouldn't it map it to a value between 0 and 1. So how are we representing it in a 2D plane?
Yes, you're very sharp. Very good. I forgot to mention this, but the authors make a simplification in the way they draw these diagrams, and they say because predicates always have the depth 1, they just don't draw it. Okay, but yeah, you are right. Very good. So other two kinds of connectives that we have are implications and negations. So we have the fuzzy variants of this for so we have I for implication and then N for negation. We'll come back to this towards the end with when discussing differentiability, because this is where all of the trouble creeps in, because all the interesting things in logic typically happen when you combine things, right? So when you want to make formulas, and if you want to make sure that things go smoothly, you need to make sure that all of these connectives, the functions that are used to implement them, are differentiable. So the next thing in logic is typically quantifiers. When you want to say something like there exists some element with such property, or for all, or of course the nestings of these connectives, we have to generalize this in the form of aggregations. So aggregators will be used to generalize both the existential and the universal quantification in first order logic. So these operators also have to be symmetric and continuous, and also some other properties in order to make sure that everything works as one might expect. So here are some examples of common fuzzy operators. So we have conjunction, disjunction, implication, and well, two kinds of implication actually. We have the girdle, the Koguin or product, and the Lukashowitz kinds. Each of these implement all of these kinds, and these, of course, they will be the specific ones that you select for your system will depend on what properties you want them to have. But this is just to show that there's a wide range of operators that are well studied, and this, like, fuzzy logic has been around for decades, really. So there's really a rich body of work that this formalism is based on for the underlying formalism. All the same for the aggregators. So typically universal You'll see things like min, if you want to essentially encode that something has to hold for the whole range of possibilities. So for all x, you'll take the minimum value, but it's not your only option. You can also do a product or the Lukashevitz variant, which takes the max of a difference here, making sure it doesn't go below 0. The same kind of thing for fuzzy existential quantification, whereas before we had min, now we have max. The probabilistic sum is very similar, but it's just taking the complement, the product, the complement of the product of the complements. So it's quite a mouthful. And the Lukashevitz one also mirrors with the other one, taking the min of the sum and 1. We'll see, as we did before, the kind of thing that we have here then is a grounding of inputs. Let's say we have two predicates P and Q, then the grounding of the predicate here again with the depth not shown. We have G of P of X, G of P of Q of Y, and then the conjunction will just be another grounding, which also doesn't have depth because it's just another kind of predicate, right? It's a kind of like a recursive thing. And this you could go on as long as you want, right? So again, as before, here we'll have a whole structure indicating all possible values, and then the output will be the way in which this conjunction is implemented. Depending on how that is implemented, as I just said in the previous slide, this will encode specific output. For quantification, we have essentially the same kind of thing. Let's say we want to encode something like there exists x, p of xy. So here we have, as I mentioned just now, the implementation or the grounding of the predicate. And then the existential one will do this aggregation, right, over all x's, and that's why now we have only values for y. And then if we tack on another quantifier there, we'll have just a single value. Okay, because this is now what's called a closed formula. If you remember your first order logic, free variables are the ones that are not associated with any quantifier. And if you don't have any of those, a formula without any free variables is called a closed formula. That formula has to either be true or false. That's why we only get a single value, right? And then here there's an interesting caveat, because depending on the properties that the aggregation operators enjoy, so these existential and the universal quantifiers, so the aggregators, depending on their properties, the semantics may or may not adequately generalize what you expect from first order logic. So for instance, if you have something like there exists x, there exists y, p of xy, so both exist or both universal. In first order logic, it doesn't matter the order in which they appear, right? It's just the same thing. It's the alternations are important between existential and universal, but for the same one, they don't matter. But depending on the properties of these operators, that might not hold. So we have to be careful, because sometimes things don't generalize as smoothly as one might expect or desire. This language has two novel kinds of quantification that makes things more interesting. One is called diagonal quantification. So it's represented by this functional notation diag of x1, x h, and it quantifies over specific tuples such that the ith tuple contains the ith instance of each of the variables in the argument. So I'll show you a diagram in just a second that will be much clearer than this definition. But essentially, it assumes that all variables in the argument are grounded onto sequences with the same number of instances, so we can do this diagonal way of traversing all possible values, because quantification essentially requires in order to be able to evaluate a formula with a quantifier. Essentially, what you're saying is that you're going to have to sweep all the values in order to see if this holds. So if there exists, you're going to have to sweep, in the worst case, all of it to see if there's a value, and for all you're going to have to sweep the whole thing to see if they all hold. Another interesting kind of quantification is called guarded quantification, and this connective quantifies only over a subset of the variables that satisfy a condition M, which stands for mask. So the definition, essentially, you have the aggregators, and then you want to evaluate if this M holds, and you're only going to evaluate the formula over those values. So as I promised, here we have the illustration of the diagonal quantification. So we have groundings of two individuals. We take the predicate, so we're trying to say for all diagonally p of x1, x2. So the way this is done is, you avoid getting the large structure, because all you want to do is traverse it diagonally, right? So that's essentially what's going on here. It's not doing anything semantically more powerful, but it is doing something much more compact. Imagine that if you have the number of features in these vectors is large, you're saving yourself essentially in order of n in space and time here. So for guarded, you can see here it's also quite interesting. If you want to do again a predicate, and you want to quantify, so there exists x, and you want to quantify, you only want the formula p of xy to be evaluated over pairs of elements, such that the first has the feature age, let's say it's the feature's age greater than the one for the second value, you're going to get something like this. See, instead of doing the whole thing, you're only going to get masked values. So the ones in pink here are the ones that satisfy this criterion, and for the white ones, you're just not going to have a value because you don't need it. So once you evaluate the quantifier, you get, as before, the values for y, and then the truth value for the closed form. So that's two new kinds of quantification for you, and that's it for real logic. Essentially, what we've done is presented a kind of fuzzy logic, right? So you've probably seen this kind of language in the past. So the question is, where do you go from here? I promised you a whole new formalism.